How's my hair look? Is this okay?
Yeah, it's good.
Is it okay?
Yeah, nice and.
Hello and welcome to our continuing series on manual machining. This week we are doing internal operations. Last week we made this part. We turned this diameter, we faced it off, we did this chamfer. So this week we're going to be doing internal operations. Internal operations are drilling, reaming, boring to size. They're what you would do if you're doing an inside bore on a part, maybe a bearing race or the like. There's two ways that we do internal operations on the lathe. The first way, the easiest way, is with the tailstock. The tailstock tends to be for drilling, reaming, or tapping a part. We can also use our quick change tool post, put a boring bar in it, and then we can bore things to size. The main difference between the two is with the tailstock, I often call it a one and done operation. With the tailstock, you're putting a tool that cuts all the way around its circumference, and it's going to drill and leave the hole complete at that point. And you're not measuring, adjusting, because the drill is what it is and it's going to come out on size. Most machinists consider drills a roughing operation. You don't use a drill to make a precision hole. Now, in the CNC world where you have carbide drills, very rigid machines with lots of testing, you can use a drill to make a precision hole. But on the manual lathe, especially with a drill like this, it's really a roughing operation. Now you can come back and you can use a reamer, which will make a much more precise hole than a drill, but it has the same limitations. Once you're done running the reamer through, the hole is at the size it's going to be. There's no second step to bring it more onto size. Whereas, just like when we were turning our diameter last week, when we are boring a hole to size, we can take a pass, measure, adjust, take another pass, measure, adjust, and we can bring a hole to a much more precise dimension with a boring bar than we can with either a drill or reamer. The other advantage of a boring operation is we can make sure that the hole stays exactly on center. If you drill a hole, especially if you have a small drill like this, sometimes it's going to wander off center. And if you then follow it with a reamer, well, obviously you wouldn't follow this drill with this reamer, but you get what I'm saying. If you follow a drilled hole with a reamer, that reamer is going to follow that hole off center. Whereas if you are using a boring bar in your tool post, it's always going to be on center because it's only turning on one side of the diameter. So you can take an off-center hole that was maybe drilled and bring it back to center with a boring operation. Okay, so that's enough of a high-level overview. Let's take a little more detailed look at these tools, and then we can move over to the lathe and make some parts. For our tailstock operations, we're going to start out by spot drilling with this number 3 center drill. We're going to follow that up with this 3/16 drill. We're going to follow that with this 39/64 drill. Then we're going to ream with this 5/8" reamer. But before that, we're going to chamfer the hole. We're not actually going to chamfer this hole because obviously it's not big enough, but when we get over to the lathe, we'll use the right size chamfer tool. So let's go through each of those steps. Why are we spot drilling with this number 3 center drill? Well, we need to spot drill because if we had went straight to this drill right here, you could imagine with this long skinny drill, as it presses into the part, it might have a tendency to flex and wander and drill off center. So, to keep that from happening, we're going to put a small dimple in the middle of the part. We're using a number 3 center drill because we're on the lathe and we have a lot of these, and it does a good job of putting a small dimple right into the middle of the part for this to follow. What we don't want to do is push it all the way in, up into these tapers. All we want to do is put a small dimple with the tip of the tool. Now, why are we following with this 3/16 drill? Well, to answer that, let's look at our larger drill. This feature on the larger drill is called the web. The web is the point in the middle of the drill where this cutting edge end flute meets that cutting edge end flute. This part of the drill does not cut very well. In fact, you're essentially just pushing this part through the metal. It's responsible for much of the cutting forces required to make this hole. So by picking a drill that is ever so slightly larger than the web of your largest drill and drilling through with this first, you reduce the cutting forces required to make this hole and help keep this hole on size and center. If you have the horsepower to run this drill through after this drill, there's no reason to step up 2 or 3 drills to get this to this diameter. Just pre-drill with a drill the size of the web and then follow with this drill. This drill is a very specific size. We've chosen its 39/64. The reason we chose this drill size is because this is a 5/8 inch reamer. 5/8 is also 625 thousandths. This being 39/64 is about 610 thousandths. So we have left 15 thousandths after drilling this with this drill for this reamer to clean up. Reamers don't like removing a lot of material. In fact, 10 or 15 thousandths is about right. What they're designed for is to create a very smooth bore and a very accurate hole, but they do not move much material. So in general, you're just going to step down to the next smaller drill size, leave a reamer about 10 or 15 thousandths to remove so you can create a nice smooth hole. Before running a reamer though, we need to chamfer that hole. Now, as I said, not with this chamfer tool, but a larger one. The reason why we're chamfering the hole is to give a nice smooth transition and guide that reamer into the hole. If we don't chamfer the hole first, chances are that reamer is going to wobble around as it goes into the hole. We're going to get poor surface finish and maybe bell mouth the hole. So those are the tools that we're going to be using for our tailstock operations. Now let's take a look at the tools that we're going to be using for our tool post operations. These are 4 single point cutting tools that we could use for our boring operation. The first thing to notice about these tools is the 2 on the left are carbide and the 2 on the right are high-speed steel. The main difference between the two is carbide is an engineered material, often called tungsten carbide or cemented carbide. It is extremely hard and good at very high temperatures. The disadvantage of carbide is it doesn't get as sharp as high-speed steel, and so tends to generate higher cutting forces. These 2 on the left are high-speed steel. They can be honed to a very sharp edge and tend to have lower cutting forces than the carbide. This carbide tool is often called an insert tool. Notice how it has a small bolt, and you can swap out inserts either when you wear an insert out or put a different insert in for different cutting conditions. Now, these inserts can be very sharp, and as technology improves, inserts can be as sharp or sharper than high-speed steel, but without the toughness. This tool here is what is called a brazed carbide tool. Once upon a time, these were extremely popular. They were the cutting edge tool in the machining industry. And there were people whose entire job was devoted to custom grinding these carbide chips and brazing them to these steel tools. These days, they are inexpensive, and With some work, you can get decent results with them, but they kind of have the worst of both worlds. You have a very hard, not well-shaped cutting edge here, and you have a normal steel or high-speed steel shank. So you tend to get a lot of flex and not very good surface finish with these tools. But they are inexpensive, and you can often get them in sets, so many people have them and make them work for them. This tool here is a high-speed steel tool, but it has interchangeable bits. So you can do custom grinds to put a groove inside your part, to turn a thread, or just to swap out high-speed steel inserts as they wear out. This tool here is a very nice high-speed steel boring bar. It can be honed to a very sharp edge. It's nice and thick to be as rigid as possible. In general, if you have one of these tools and can fit it inside of a bore, for the type of lathes we have in the shop, this is going to give you your best result. Okay, that's enough of this. Let's go over to the lathe and make some chips. Here we are over at the lathe. I need to get my stock in the chuck. And first thing I need to do, as we talked about last week, is I need to get my tool height set. I'm going to face the edge of the part. You never really want to drill into a non-faced part. This is saw cut. It could be at an angle and it could really drive your part off center. So it's a good idea to always face the part before doing any drilling or boring operations. So I'm going to check my tool height, and it is way low. So let's just eyeball it to somewhat near center. Try that again. Now it's high. Back off. Let's do that so we don't go too low. Somewhere around there. We'll see when we face it. This is a 1.5-ish diameter part. Let's measure it. No, 1.5. I was right. It's an 1.5 part. So if we use our cutting speed formula, that's 80 times 4, so it'd be 360 divided by 1.5. So we're somewhere around 250 RPM. But we also need to realize we're just doing a facing operation, and the diameter is going to get smaller and smaller as we go to the inside of the part. So I'm probably going to pick somewhere in the middle there. I think I'm going to run this at about 350 so that we can have enough speed as we move into the center of the part, and off we go. One of the things you'll notice is I'm not getting a complete cut all the way around, even where I've already taken a pass. So rather than waiting till I get all the way into the middle to notice that, I'm going to come back out and take a little bit of a deeper pass so that I don't have to wait till I get all the way into the middle to come back to take another pass. Looks like I got my tool mostly on center. Let's back our carriage out. Now this has left a sharp edge right here. I know I'm going to have to break that edge eventually. So I'm going to go ahead and break it right now, just with a file. Now you may be used to running a file with your right hand. On a lathe, you're going to hold it in left hand. being careful to keep it away from the chuck jaws. Just gonna drag it over the edge a couple times. No more sharp edge, so I'm not gonna cut myself while doing the rest of the operations. We have our part faced and we are ready to start our drilling operation. We need a drill chuck in here. Well, remember that all we have to do is back the handle all the way out to remove our center. Run this back out. Now we have our 3-jaw chuck in here. Let's remove the key. And we are going to start with a spot drill. Now, our part is 1.5 inches, but our tool is really small. This is about 1/8 of an inch tip on this drill. So we are not going to set our RPM based on the size of the part. We're going to set our RPM based on the size of the tip of the tool. If we were to run this at the 300 RPM that we faced this off at, we would more than likely break the tip off of the spot drill. It's probably one of the most common mistakes that happen with a center drill. So what we're going to do is we are going to run the lathe at about 1,000 RPM while we center drill this hole. Now we're going to feed slowly. We want to see chips being made, but we're not feeding too fast because we don't want to break the tip off of our center drill. For this, all we want is the tip of the center drill in. We're not going to push this tapered section into the part. All we want is a little hole made by the tip. So now we're going to go with our small pre-drill that is about the diameter of the web of our larger drill that we're going to follow. Now this is a jobber length drill. Had we not put that spot drill in, it probably would have wandered all over the place. Now, how are we going to tell how deep we're going? This is one of the disadvantages of using the tailstock, but it's something you'll get used to, is there's no digital readout for the tailstock. There are two ways to tell how deep you're drilling. One is we have a scale right here on the barrel of the lathe, and we can watch that. And then we have a dial, just like we have on the cross slide and just like we have on the longitudinal feed, to see how deep we're going here. So I'm going to pre-drill 3/4 of an inch is what I'm going to do on this. And so what I'm going to do is I'm going to set my scale at 1 here and 0 right here. And then I'm going to push this just about up against the part, right like that. And then I'm going to just hand feed with the dial till I read 3/4 of an inch. Since this is just a pre-drill hole, I don't have to be all that accurate. I'm going to stick with the 1,000 RPM. I have some cutting fluid here. Drilling holes in steel, it's always a good idea to use some cutting fluid. It's going to keep your part cool, it's going to keep the tool cool, and it's going to help the chips to move out, up the flutes and out of the part. Basically makes everything go easier if you have some cutting oil on there. Do you see as I was feeding in with a hand wheel and pushing the drill into the part, I could see the chips working their way out. You want to keep a constant pressure. You want to see the chips working out. And chips of about this size for this size drill are good to see. If you go too slow, all you're doing is rubbing the tool and things are going to heat up. And so you want to see chips moving out. You don't want to see little fragments. Now, it's going to depend on the material. So you want to feed fast enough that you see the chips working their way out. The chips also effectively remove heat out of the part. So if you're not seeing chips, you're probably just rubbing the tool and things can overheat. Okay, so that was about 750 thou. You'll notice as I was drilling how I was drilling in and then backing out and then drilling in and then backing out. The point of that is to let the tool cool off a little bit by pulling it out of the hole, getting some air exposure to the tool, and also to pull the chips out. There's what's called chip recutting, which is heats up the part, wears the tool, and that's when the chips stay in the hole and you just keep driving the drill in. It just causes a bunch of heat and tool wear. So you want to periodically pull the drill out, clear the chips, and then put it back in. It's called peck drilling. So I've drilled my pilot hole to 3/4 inch. Now we're going to swap out the drill again. To our big guy, our 2960, what is this? 39/64. There's going to be some cutting forces here. Let's talk about this for a second. The cutting speeds for tools are ideal conditions. Oftentimes what you're talking about is a perfectly sharp drill in a perfectly rigid machine. CNCs with a brand new tool approach those numbers. You can always go slower than your calculated speed. In a situation like this, more than likely, I'm going to start out quite a bit slower than whatever I calculate. I've got a lot of stick out. I'm on a 3-jaw chuck. I don't know if this drill is perfectly sharp. I'm going to slow this thing all the way down to about 200 and start taking a cut. And if it's behaving really well, I can speed it up a little bit. It's one of the advantages of these, the variable frequency drive on this lathe. I can just turn the knob a little bit and speed it up. If it's misbehaving, I can turn it down. But always start too slow and then increase the speed. There's a phrase that machinists like to use. I think it was originally referring to cars, but speed kills, in that if you overheat a tool, it will kill it immediately. But if you go too slow, you're not causing any harm. So I'm going to start out, and once again, I'm going to set my scale right here at the 1 and my 0 on the hand wheel, and then I can pull this up right to the edge. Yoink. And lock this down. I need to shift my gearbox into low, and I'm going to turn this all the way down. It's about 200 RPM. Let's see how that cuts. Not hearing any squealing. I'm getting some nice chips off it. Chips are coming off of both sides, out of both flutes, so it's a reasonably balanced drill. I'm already a third of the way to my final depth, so I'm probably just going to leave the speed alone because it's cutting and it's only going to be about a minute or so until I get to my final depth. So why mess with something that's working? So that's 300 thou. Get some more oil there, get some oil inside. Just past 500 thou. going to peck a little bit more often as I get deeper because I've got to pull the chips farther out and things are probably starting to heat up a little bit. There's our drilling operation. Tool's a little bit warm, but not too hot. Okay, so I have a problem here. My 5/8 reamer doesn't fit in my 3-jaw chuck, which is kind of a problem, but in a way, it's kind of a good thing. Drills are made to go in a 3-jaw chuck. They tend to have a slightly undersized shank, and they're not really a precision surface. They are, but they're not. Once that you put anything in a 3-jaw chuck, it's really no longer a precision surface. A reamer, this is exactly this. I'm not sure exactly what size this is, but they're machined to a precision dimension, probably 1/2 inch, and you can consider this a precision surface. Once you put in a 3-jaw chuck, sometimes they'll spin in the 3-jaw, it damages the surface, and then you can never put this reamer in a collet again. So we're going to want to use something else, and what we're going to do is we're going to use a Morris taper adapter, and we're going to get rid of this 3-jaw chuck, and we're going to put it directly into the tailstock. But before we do that, we need to chamfer this hole. I'll just leave it at the same RPM as drilling at. You'll notice how slow I was feeding with the chamfer tool. This chamfer tool is a single edge cutter. This is the only edge that's cutting right here. And it's cutting a fairly big diameter and taking a fairly deep cut. In fact, the deeper you go, the deeper of a cut it's taking. So you don't want to force it in. It'll cause chatter and just damages the tool. So you want to feed nice and slow when using the chamfer cutter. So we're done with the 3-jaw, and we can ream. So this reamer has a Morris Taper 2 adapter on it. We've talked about various tapers, various self-grabbing tapers, both over on the mill and on the lathe in this class. Morris Taper is one of those, but we'll notice too small for our tailstock. So we have an adapter sleeve. The inside is Morris Taper 2, the outside is Morris Taper 3. If I line the tabs up, and they stick together, and then I can put this in the tailstock. If we put that out far enough, and there we go. So this provides a much more concentric, much stronger grip than the 3-jaw chuck. So this is really ideal right here. So now we are set up to ream. We need to talk about our speeds and feeds for reaming. The general rule of thumb is 1/2 to 1/3 the speed and twice the feed. This cut tool is not going to be removing much material. We can pretty much drive it through really fast on feed as we're going, but we're going to be running the spindle really slow. Since we did this about 200, let's run our spindle about 100 as we're reaming this. And we're going to want to use a lot of cutting fluid. Run that up at the end, lock our tailstock into position. That ought to do it. Okay. You can see how much faster I'm going than when I was drilling. We have hit the bottom of our hole. And that should be a pretty precise 5/8 hole. Once again, we've talked about the disadvantages of measuring the inside of a bore with calipers, but that looks pretty much dead on 625 to me. Okay, let's get our reamer out of our tailstock. Pulling that out like this. Remembering to put the live center back in. We never leave the tailstock empty in case it gets chips. And then we can just slide the tailstock out of the way because we're not using it anymore. So this taper adapter has a slot in it to help you separate the adapter from the sleeve. Okay, just give me a few seconds to set up and we'll do the boring operations. Okay, so first thing we have to do is put our boring bar in our quick change tool holder. So I've chosen this high-speed steel one. As I said, I like it because it's sharper and it's going to create fewer cutting forces and hopefully give us less chatter and better service finish. The tool holder I've chosen has a slot in it right here. This is designed specifically to hold round tools like this. Now you can put normal cutting tools in here as well, but they're specifically optimized for holding these round tools. So I'm going to drop this in the slot, and then I'm going to tighten my set screw down and tighten my set screw down. Now this angle here, I want it to be flat. I could even have it a little bit up, but for the most part, I want it to be dead flat. So somewhere right around there. So I'm going to tighten that down. Once again, thinking about stick out, minimizing stick out so I can maximize rigidity. Now, just like on the when we're doing outside turning operations, I'm going to have to set my angle and I'm going to have to set my height. And I've just made a mistake here. Because I've set this up like a normal tool, I'm going to have to flip it around to the other side of the quick change tool post holder. That's actually tradition. I do that every time I set up an internal boring tool. We want to set it over here. It'll make sense why this is happening in just a second. So once again, it's in the slot. Tighten these down. Get this mostly level. Tighten that down. So now, since this is a boring operation, we are going to run on this side of our quick change tool post. Now, we need to set height and we need to set angle. So let's do our height first. There's a few things that come into play here, but let's start out setting our height just like we do when we're doing turning operations. Only now we need to do it on the back side of the part because of the way our tool is arranged. But we can use our 6-inch rule and do it just like so. It is too high. I'm going to take it right there. So let's talk about height for a second when we talk about internal boring operations. When we were doing outside operations, talked about how we can't be too low because it might dive under the part. We can't be too high because it won't cut. The cutting edge doesn't make it up to the part. Internal boring operations are a totally different ball game. We can actually be too high. and it's just going to move up the curve, but we're still going to have the relief on the underside of our cutting tool, so it's still going to cut. So in general, we can be too high on an internal boring operation, and it's still going to cut. It's going to affect the relationship between how far we move the tool and how much it actually cuts. In fact, the DRO, if we're way too high, is no longer going to read accurately. But it can be a good way to combat chatter. If your tool is too low in an internal boring operation, very likely you will get chatter. If it's too high, you are less likely to get chatter, but it can cause dimensional problems. But basically what I'm saying here is if you're fighting chatter, if you can't get rid of chatter, one thing you can do is try raising the tool ever so slightly, and it can reduce that chatter. So now let's talk about angle of the tool here. Just like on a cutting tool for an external operation, you want the thing that is doing the cutting to be sticking out farther than everything else. So you want this angle to be receding back, and you want this angle to be receding back. Because what we're going to do is we're going to feed to the bottom turning, and then we're going to face the bottom of the part off. And if this angle isn't receding, it's going to drag across the bottom of the part. And if this angle isn't receding, it's going to drag across the side of the part. Now, the other consideration you have is if you turn this at too much of an angle, your tool can actually run into the bore. So those are the three considerations when setting up angle. And I'm pretty happy with the way mine is right now. I think I might just turn it back a tiny bit this way. Not much. I just need enough to have this tip sticking out farther than that. There we go. So now we have this set up, we have our height set up, we have our angle set up, and I think we are ready to start making chips. Just like with our outside turning operations, we need to set our Z offsets, and we have to zero our Z and zero our X. We're going to be doing it a little bit different this time. So let's start off and just zero our Z. And so that we don't mess up the outside of our part, I'm just going to very gently run into the side of the part. So I want that on 0, and I've zeroed my Z. Okay, so just like outside turning operations, we're going to take a pass, and then we're going to measure it, and we're going to set our X. So I'm going to back it off till I just barely hear it touch, and then I can zero my X, back it up just a little bit more, move in here, and let's take a pass. This is about a 15th thou pass. Watching my DRO so I don't crash into the bottom of the hole. And back it out. Okay, so I've got 640, which is about what I would expect, because we took a 625 thou hole and then took a 15 thou pass. We're going to do something a little bit different this time. Rather than just zero our X, we're going to hit this button. So now the LED is lit up down at the bottom where it says set. Now what I can do is I can hit this button next to the X, and I can enter 640 thou and hit enter. So now what I've done is I've told the DRO the size of that hole with this tool. So now you notice what I can do, Z is still zeroed at the face, but now this is going to change as I move my cross slide. So we're going for a 1-inch hole. I can just watch the DRO and watch the changes rather than having to do the math in my head each time. Now I'm not going to trust that DRO completely. I'm going to stop a couple times and measure on the way, but this is going to allow us to rough a whole lot faster and then fine tune our measurements and the DRO setting without doing a whole bunch of math in our head. So that last one was 640 thou. Let's take a 20 thou pass now and take that up to 660. Just like with turning operations, I'm keeping my hands on the handles the whole time, my foot near the brake. The last thing you want to do is things to go sideways and you're not in a position to take control of the lathe. I'm going to try a little deeper pass now, see what this will take. This pass will be about 800 thou, and I'm probably going to measure again. Okay, let's measure that and see how we're doing. I'm reading 794, 793. So what we can do now, since we have this set as set, we're going to correct our DRO. I'm going to hit that again. I'm going to enter 793, hit enter, and now I can keep taking passes. Probably going to go right up to 900 thou. And then I'm going to change my feed to get better service finish on my finishing passes. And this pass makes 900 thou. Okay, now I might be a little bit oversized. I'm reading 905 thou. Let's use a different way of measurement, see if we can get that a little bit more accurate. This is what's called a snap gauge, bore gauge, telescoping gauge. Way this works, we snap it in here, we loosen it up, we put it up at an angle here, and then we tighten this handle. Now as we slide it down, the spring tension in this is going to find the maximum diameter. And then we can measure that with a micrometer. So once again, I'm going to put that all the way in. I'm going to put it in. I'm putting it up at an angle. And then I'm releasing the tension. And then I'm adding some tension. And I'm doing my best as I slide this down to not control the way it goes down. I'm just going to shove it down and then let it fall into my hand so that the spring tension will find the largest diameter of that part. And then I can take and I can measure this with a micrometer. And you want to, when you measure with a micrometer, find exactly the maximum diameter without compressing the snap gauge. So I'm taking my micrometer, holding it like I always do, putting this up against this surface, and I'm sweeping it back and forth until I just barely feel it make contact. And then I'm going to back off until it'll pass through. So that's my measurement right there. And sure enough, I've got 903 thousandths and 5/10. Okay, so now what I can do is I can 0.9035, enter. So now I just set my DRO to what I measured with this. Now that's not the end of our measurement, because I'm going to go and change my feed. I'm going to slow my feed down for these final passes, and I'm going to cut it in half. So this is going to be 4 thou per rev. And I'm going to take these passes at 20 thou each. That's going to be 5 passes of 20 thou, and we're going to see how close we can get to that 1-inch diameter. So the DRO says 940. Calipers say 940. Okay, 3 passes of 20 thou, and let's see how close we get. Second to last pass. Time for the last pass. Here we go. Going to go all the way up to 1 inch. Doing that same 20 thou that we've been doing for all of our passes. Here we go. When we hit the bottom of the part, we're going to feed into the bottom and then drive across, slide apart to square up the bottom and back out. And let's get that right on. Well, with calipers it looks pretty much dead on. It's a little hard to tell sometimes. Call that dead on. Really close, really close. We might be a couple thou oversized on that.